So what we're going to do here is a quick question on quantum gates and quantum states. So let's test this out. Now it's working. So what do we have here? We have a quantum gate. What does a quantum gate do? You can apply a quantum gate to a current state. This is a current state represented by a vector. So just some arrow in a certain direction in three-dimensional space in this um, occasion. So in basics of quantum computing, we have X gate, a Y gate, and a Z gate. Each of these rotate the um, the arrow that I was talking about around the x-axis, around the y-axis, and around the z-axis, pi radians. So that is 180 degrees around the respective axis. So that's pretty simple. So what are we trying to do here? We're trying to apply. This means the current state. This means we're trying to apply y to the current state. So we're applying a gate to the current state, like you could do in classical computing. Apply a gate to some set of bits. You can do an XOR like that with two kind of bit strings. But anyway, nonetheless, we're applying y to this state. So this is a state. So this is the zero, represents the zero state, and this represents the one state. So you can get the probability that it will be a zero or it will be a one when it's measured. So it's in superposition before you measure it because you don't know which one it's going to be. And what determines which one is going to be upon measuring is a probability. So the probability that it's going to be a zero, terrible arrow, whatever, is denoted by this value here. So that over 2, oops, over 2, and we square this. So we apply the square to the top and to the bottom. So if we apply it there, we just get rid of the root. If we apply it here, we get a 4. So that's 3 over 4. So the probability that it's going to be a 0 when we measure it is 2 over 4, so 75%. And if we do the same over here, so we apply square root, 1 squared is 1, 2 squared is 4, so we have 1 in 4 chance of getting a 1. So overall, we have 75% chance of getting this one, a 25% chance of getting this one. And, they notice that they add up to 100%. It's a pretty basic probability. But that was a side note. Now we'll be applying this gate to this state. So I'm not going to write out this each time because it's kind of hard on fucking MS Paint, whoever owns Paint. X equals, we're going to distribute the y into each side because that's what you have to do. So we get 3 over 2, then we distribute the y, and then we still get this guy, so the 0, plus a half y, and then the one state, create the one state, but in brackets, you already need that, because we've already put the y in. Okay, what do we do next? So, what is y 0 in this case? Well, we can represent it in a matrix like this. This column will represent is the same as this. This column is the same as 1 applied to dy. So this is the case we're using. So this side is the 0 and this side is the 1. So what we're going to do is take this and replace it in for this. So we're going to have the same number. We're going to replace this guy 0i, because that's the first column of the gate we are applying to this state, plus a half. Then we get rid of this one like we did here, and we use the second column because it is the one step. So minus I 0. Okay, what can we do here? Well, all we can really do is factor out the I. So the I is factored out like so. Should 0. So why can you factor out the I here? That might be a question you have. So when you multiply it in, I by 0 is 0. So that's the same at the top as it already was. 1 by I is I. So that's the same as it already was. They're the same thing, just factored out in a different kind of way to write them. Same here. Minus I by 1 is minus I by 0 is 0. So it's just a different way to represent. Okay, now what can we get rid of? Okay, well, if you've done a tiny bit of this before, you'll represent this as representing the one state, and this representing the 0 state. So what we can do, forgot the boost, 3/2. This is the one state, so we go 1, then we plus a half minus I, and this is the 0 state. So this is the new state of the qubit. Now that we have applied this gate to it, and it has transformed it pi radians on the y-axis. So if we did the same for the z gate, we would do pi radians, which is 180 degrees, around the z-axis, and the same for the x-axis. Apply the x-axis, it rotates the vector around the x-axis by pi radians, 180 degrees. Okay, so this is the answer. Don't think I've made a mistake. If I have, leave a comment. Yes, thank you.